In this section, we're going to talk about how do we actually prevent the routing loops. So we talked about what are the potential cases where maybe the metric is wrong or the administrative distance is wrong. You go from a high distance to a low distance and then you try to come back and you cause a loop. Well, what are the ways that we can actually fix the problem once we figure out that is the issue? So a lot of these sections, when we're looking at on the CLI, this is what we're going to be focusing on, is what is the actual strategy you need to use to prevent the loop once you've found it. And the big issue is going to be, how do you even find it to begin with? Now, the big thing, again, to think about here is where in the topology are multiple protocols meeting. So we have in our example cases that router 1 has OSPF and EIGRP, and router 3 also has OSPF and EIGRP. This is immediately a red flag that there could be a potential case, but again, not that there is a problem, just that this is a potential case where someone could make the wrong decision and then route the packet in the wrong direction. So depending on whether we're doing mutual redistribution in both places, this could be a potential problem area. But again, there's not really general rules that you can apply onto it. So the general idea is that we need to protect whatever protocol has the higher administrative distance where the two protocols are meeting. Because if I'm coming from RIP, which is a distance of 120, and I go into OSPF at 110, if the route comes back around somehow and it now has a lower distance, I'm no longer going to listen to the original advertisement. I'm going to take the new advertisement and then either cause a route or a loop in either the control plane or the data plane. So the problem to begin with the administrative distance is that the higher AD routes have a chance of getting fed back, which is what we call route feedback, via the lower administrative distance protocol. So basically what we need to make sure happens is that whatever is the original source protocol, that needs to be the one that is preferred. But the issue is that it's not going to be preferred by default, because we look at the lower administrative distance to take the preference. Now, in some cases, we might see that this has the end result of suboptimal routing. So you might go the wrong way to get to the destination, but as long as you get there, that might be all that we care about. Really depends on what the individual scenario is. Now, in a real design, of course, you would always want to choose the optimal solution, but within the scope of the lab exam, it just might be that you need a solution in order to get there, not that you need to route to the closest destination. So, for example, in our particular case, let's say that router 3 routes this direction in order to get to router 7. As long as the question doesn't say don't do that, then it might be fine. But if the question specifically says that router 3 should go this way to get to 7 and 1 should go this way to get to 7, but everyone else also should have reachability, then that's some other attribute that we need to take into account when we're solving the problem. But under most case situations, they're probably not going to say that, because the topology in general will get too complex that you cannot meet all conditions at the same time if they put too many restrictions on what you can do and what you cannot do. So we're mainly going to be focusing on just reachability in general, not necessarily optimal reachability. So again, we talked about two different types of loops. We have metric-based loops and we have administrative distance-based loops. The tools that we use in order to solve these problems are going to be different, because an administrative distance-based loop, we are not able to fix this by using something like a route tag. Where the metric-based loops, generally we're not going to be able to fix this based on using only the administrative distance. Again, the overall logic of this is that we don't want the routes from the protocol X to be fed back to that protocol through another point. So we can stop that either by doing a distribute list at the interface, maybe a distribute list under the process. We could do a metric filter to say, prefer your own internal metric versus an external metric. So there's a lot of different ways to solve the problem. But the big thing is, first off, we need to figure out what is the problem to begin with. Now, there also are some automatic tools. For example, in BGP, when we redistribute from BGP into IGP, the redistributed routes are automatically going to be tagged with the BGP AS. This means that when the routes come back, if we now try to redistribute IHGP back into BGP, we can prevent the loop by matching on the tag value. So we'll see in the next sections as we actually go through the examples, this is where we're going to look at when do you need to look at debug IP routing versus looking at a trace route. And then once we figure out where the problem is, do we fix it by changing the metric, by changing the distance, or do we fix it just by filtering out the route completely? So now let's talk about what specifically is going to be our first case. The first case is going to be where we have two different routing protocol domains. We have router 1 that is connecting EIGRP to OSPF, and we have router 3 that's connecting EIGRP to OSPF. There's going to be 3 different redistribution points. Router 1 is redistributing EIGRP into OSPF. Router 3 is redistributing OSPF into EIGRP. And router 9 is doing connected redistribution into EIGRP. So if we look at the config, it's a very simple config. There's not really going to be a lot of tricky things that are going on here in the redistribution. Router 1 is simply saying redistribute EIGRP 100 subnets. Router 3 says redistribute OSPF, we're giving it a metric value. And then router 9, we're saying just redistribute connected. Again, when we're redistributing connected into EIGRP, it's going to pick the vector attributes from the connected link already. So in this case, you don't have to set a metric. You can set the metric if you want to, but otherwise it's going to choose whatever the link already directly has. So I want to give you guys some time to think about this before we actually look at this on the CLI. So we're going to take about a 20-minute break now, and I'm going to leave the topology up here. And the question really is there going to be a problem? Well, there is going to be a problem. What is the problem? Why is it happening? And then what are the possible solutions? Because there is more than one way to fix this problem. So it's not to say that your solution is right and someone else's is wrong, or one is better than the other. It's just the end goal of reachability. That's ultimately what we're trying to get to. So we'll talk about more than one solution for this, because especially within our scope, you might get to the exam and they say, don't use tags in order to fix this problem, or don't change the administrative distance, or don't do whatever XYZ, and then we need to figure out, based on whatever else is left, what are the rest of the options that we have. So again, we'll take about a 20-minute break here, and then when we return, we're going to look at the actual example of what is going on with the redistribution here, why is the problem there, and then again, what are the possible solutions.